And hi everyone, and thanks for coming. I'm Dan Mingzhou from Peking University, and today I'm glad to be here to introduce our recent work, detecting floating point arrows via atomic conditions. So let's start. Before the detailed introduction, I would like to first highlight our result first. Last year, DEMC was proposed for detecting floating point arrows, and it cost about 8 hours for analyzing 49 functions from GSL. And our tool on the same benchmark only needs 21 seconds for analyzing them, so which is more than 1,000 times faster, while at the same time, we detect 40% more floating point arrows. And this is the outline of this talk. In the first section, I'm going to introduce floating point arrows and most existing approaches to do that. And here is an example. We know that there are always floating point arrows, and sometimes the arrow can become significant. And here, like this example function contains only 4 basic operations here. When we try a specific input like 10 to the minus 7, the result becomes significantly inaccurate. It only contains 3 valid digits. So how do we find this kind of erroneous input? Like the existing approaches, most of them treat the floating point program as a black box, and they heavily depend on the Oracle F. Like they first calculate the floating point result, and they also calculate the Oracle result, and to get the error of this input and repeat this procedure to find the erroneous triggering input. And also, since the high precision since the Oracle is only conceptual, most of them use the high precision program to simulate the Oracle. But at the same time, we notice that the high precision program is not a silver bullet. It brings several difficulties that are not solved yet, and which we will discuss in the next section. We find that using high precision types is very expensive for 2 reasons. The first one is they're expensive in computation cost. Even quadruple precision are more than 100 times lower than double precision, and for MPFR, the overhead further increases. And the second one is they're expensive in development cost because we cannot simply change all variable to high precision types to get a more accurate result due to the existence of precision-related operations and precision-specific operations. And since the time is limited, I'm not gonna discuss about these 2 kind of operations, but we know that this kind of operations need to be manually found and handled to get a more accurate result. So it's kind of expensive in development cost. And so it leads to the need for an Oracle-free approach. And we know that if we have the Oracle, we can distinguish this input with their arrows. So the question is, how can we analyze the floating point program without Oracle, since we have no idea whether result is accurate or not? And this question leads to our approaches in the next section. In the third section, we're gonna discuss the concept of atomic condition and our analysis based on atomic condition and our approach atom. We start from the component of a floating point program. Like a floating point program can consist of atomic operations, such as basic arithmetic and basic functions, which we define as an atomic operation. And we also know that the error on this atomic operation are guaranteed to be small by some definitive documents. So why does the significant error still exist? We find out this is because the error is not just introduced and propagated through these operations, but also significantly amplified by certain operations. And to understand how these errors are amplified, we adapt the concept of condition numbers here. The condition number is a concept from mathematical analysis and numerical analysis, and it measures the ratio between the error in the input and the output. In other words, the condition number measures how much the relative error will be amplified from the input to the output. For example, the condition number on cosine x is x times tangent x. And for different value of x, the condition number, also the error amplified factor, will be different. And by focusing on condition number on these atomic operations, we can know that during an execution, which operation may amplify the error and become risky. Here comes out the key insight of this paper. We define the concept of atomic condition as a condition number on atomic operations. By leveraging atomic condition, we can analyze floating point program in a white box manner. And we can measure how much the relative error is amplified by atomic conditions, and we formulate that atomic conditions are the dominant factor for floating point errors. Since atomic condition only needs native floating point types to compute, we can get rid of high precision types, and which will significantly accelerate our analysis. Here we use the example to show the relation between the atomic condition and the floating point errors. This is the example function and also an example program here. We know that at the operation level, for each operation, the error in the input will be amplified by atomic condition, and also add an introduced error that together becomes the error in the operation's output. And for a specific input 10 to the minus 7, we check this step by step. In the first operation, there is no error in the input. Atomic condition is very small, so there is only a very small introduced error in the output. And in the second one, the input contains a very small error, but the atomic condition here is very large, so the error is amplified significantly by this operation and become a very large error in the output. And in the third one, there's no error in input, condition number is 1, so the output contains a very small introduced error. And in the last one, there is a significant error in the input, and condition number here is 1, which means the error will just pass to the output of this operation, which is also the final result of this program. And how to calculate atomic condition? Like we have the condition, definition of condition numbers here. It involves a derivative of the fx. And since we define the atomic condition as the condition number on these atomic operations, and their derivatives all have mathematical expression, we can use pre-calculated formula to calculate them. Like for cosine x, their atomic condition is x times tangent x, and we don't need any other high precision thing to do that. We can directly calculate it with native floating point types. And by analyzing this formula, we can distinguish these operations into two categories. The first one is potential unstable operations, such as addition, cosine, and log. For this kind of operations, their atomic condition can become significantly large if the operand falls into the danger zone. And for the other one is stable operations, such as multiplication and square root, because by analyzing their formula, we find that the atomic condition on these operations are always less than or equals to 1. And all the previous discussion lead to our final approach here, atomic condition guided search. This is a dynamic search-based approach. And in this approach, we first generate input and track its execution and calculate the atomic condition on each operation. Our goal is to find the largest atomic condition on each operation. And as the search continues, we may find some operation involves a very large atomic condition, and it may lead to erroneous intermediate result and may also lead to erroneous final result. And we use an evolution algorithm here to act as a search module, and also other search module can be easily interrogated. So in the last section, we're gonna discuss how effective and how fast is our approach. We conduct our experiments on the GSL, and we find that 42 of 88 functions have significant errors here. Like here is the histogram. We find that some of them on the left hand do not have severe floating point error issue, and on the right hand, there are some of them, like 42 of them, have severe floating point error issue. Also, when compared with the state-of-the-art technique, like DEMC last year, our approach finds significant error in 8 more functions, which is 30% improvement, at the same time incurs no false negatives. At the runtime cost, Atom needs only less than half seconds for analyzing one GSO function, which is several orders of speed ups over the state of the art, which also makes our approach much more practical. So finally, some take-home messages. In this paper, we introduce Atom, which is a super fast and effective technique for detecting floating point errors. We also introduce the concept of atomic condition, which we believe is a powerful tool for analyzing floating point programs. And it brings several advantages, such as oracle-free, native, and informative. Because of these advantages, we expect atomic condition to have a broader applications, such as debugging, repair, and synthesize. That's all. Thank you.